This is section 13.7, and we're going to do our first example in our notes for Stokes Theorem. Before we do Stokes Theorem, however, we're going to do this problem using techniques from section 13.2. So we're going to evaluate this particular line integral over a vector field where the vector f is negative y squared x z squared, and then the curve is going to be the intersection of the plane and the cylinder. So what we're going to do first is we're going to set up a parameterized equation for the curve, and the best way to do this is to use cosine of t for x and then sine of t for y. And then if you notice in the problem we have y plus z equals 2, so we're just going to make that z equals 2 minus y, and since y is sine t, that's going to be 2 minus sine t. And we're going to need our derivative, because again what we're going to do is use the equation given to us in the problem to calculate this particular integral. So we take the derivative and we get negative sine t cosine t and negative cosine t. And so we have our r prime. Now what we need is our vector f in terms of r of t. So again, we've been doing this a fair bit in this chapter. So we're going to take our x value, which is cosine t, we're going to put it in for x, the middle term, take our y, put it in for y in the first component, and then take our z, put it into z for the last component. So what we have for our vector is negative sine squared t, cosine t for the middle component, and then 2 minus sine t squared for the third component. And then let's go ahead and simplify that last component just so that we're all set to go for the integral. So we have 4 minus 4 sine t plus sine squared t. Okay, so our integral then will be from 0 to 2 pi, because remember, if we're using our parameters that we chose for this particular curve, we're going to go all the way around this curve, which is going to be 0 to 2 pi. So that's going to be our parameter for t. And then we're going to take our vector f that we developed using the vector r, and then we're going to dot that with our r prime vector. So we have negative sine t cosine t and then negative cosine t dt. Okay, I'm going to go ahead and pause this and set up the antiderivative, and then we'll continue. Okay, so here's our simplified dot product, and what we're going to do is take the antiderivative of each of these parts. Now, before we do that, we're going to need a use substitution for this particular piece as well as this particular piece. So let's go ahead and do that off to the side here. So we have the integral of cosine t sine t dt, and in this case u should be sine t, du should be cosine t dt. So we have the integral of u du, which is 1/2 u squared, and we'll convert back, so what we'll get is 1/2 sine squared t. Don't forget, we're going to have to ultimately multiply that by 4. We're just doing the work initially to do our u subs. And then for the other one, we have sine squared t cosine t dt. And again, u is going to be sine t, and du equal to cosine t dt. And so we have u squared du, which is 1/3 u cubed, and that will again go back to 1/3 sine cubed of t. And we will be multiplying by a negative as well in that case, because again, we were just doing the basics. Okay, so what we have then for our antiderivative is going to go back to, if we're dealing with sine cubed t, we had all those formulas that we've talked about a fair bit, and we wrote down in chapter 12. So that one's going to be negative 1/3 2 plus sine squared t times cosine t. Again, those are from our textbook, so you should have those written down somewhere. And then for cosine squared, we have 1/2 t plus 1/4 sine of 2t. All right, so what I've done is I've taken the antiderivative of sine cubed t, we get all of this. Cosine squared t, we get all of that. Then we have our next one, which is minus 4 cosine t. That's going to be minus 4 sine t. Then we have our next one, 4 cosine t sine t, which again, we did our u sub. So we're going to have 4 times 1/2. So we're going to have 2, positive 2, and then sine squared t. And then our last one, again, we're going to subtract 1/3 sine cubed t. So minus 1/3 sine cubed t. Okay, we are ultimately going to evaluate this from 0 to 2 pi. Now, it's a fairly long antiderivative, but keep in mind that both sine of 2 pi and sine of 0, or I guess in this case, sine of 4 pi, those are all 0. So we're actually going to simplify it down a great deal. Our first little bit here will be negative 1/3 times 2. Cosine of 2 pi is 1. So that's just going to be negative 2 over 3. And then we have 1/2 times 2 pi, which is just pi. And believe it or not, the rest of it's 0. And then we subtract, if we plug in 0, sine of 0 is 0 and cosine of 0 is 1. So what we get is negative 2 over 3. And the rest of that is 0. And then what we get ultimately here is pi. So that is the value of this particular line integral. That's using old techniques from section 13.2. So now what we're going to do is we're going to take a look at this using techniques from our current unit, and we're going to use Stokes Theorem. So with Stokes Theorem, again, what we're doing is the exact same initial integral. We're still calculating the same thing here, the line integral c of f dotted with dr. And if we go back up to our surface, the reason that Green's theorem is not utilized here is because this surface is in space. The surface is not flat on the xy plane, and so because of that, we're going to want to use Stokes theorem. And again, we could have done it in the way we did for part A, but again, it's just good to have options. I don't want to hopefully convey the connection between all of these different theorems and different techniques and everything else. So we're going to say by Stokes theorem that this is equal to the double surface integral of curl f dotted with ds. Okay, now our surface again is z equal to 2 minus y, and we have our restrictions and everything. Let's go ahead and calculate curl f. So we have curl f. I'm going to pause this and set up the cross product. Okay, so again, what we have here is curl f, and our vector curl f is going to be 0, 0, and then 1 plus 2y. And again, that's what we're utilizing here. So this is where I think some of the most complicated things come into play. And really, I guess it's not complication, it's just interpretation of all these formulas. So what we have here is a vector curl f, and it's dotted with ds, and s is a vector. So this is a surface integral over a vector field. And the techniques we use for anything like that come from section 13.6. So we spent a ton of time with 13.6 talking about the different techniques. So here's what I'm trying to say. If you have, this is from section 13.6. So if you have a surface integral f dotted with ds, that's exactly what we're really talking about here. That is equal to either the double integral over the region D of f dotted with the cross product between these two vectors, dA. Okay, so we've taken the ds piece and we've put it into dA, so it's an actual doable double integral, or it is going to be the double over d of negative p multiplied by the partial of g with respect to x minus q times the partial of g with respect to y plus r, and then again with respect to dA. Now remember, this one here is for a surface z equal to gx. So that's exactly what we have here. However, okay, back to this this middle one. This one is if we were to, find some sort of parameter for our surface. Well, we could take our surface and we could potentially parameterize it. It just seems like it's more work than it's worth because, again, even though it's okay to choose a set of parameters for this, we have it set up and we have an option for this type of formula. Now, it all goes back to the idea that this is all from 13.6, but remember, in our particular context, this is simply just curl F for this problem. So once we set up our problem and we're utilizing Stokes theorem, curl F is simply just a vector. And so we're going to go back to section 13.6 and utilize techniques in order to solve it. So again, our options here are either to set up an additional vector that parameterizes our surface, or we utilize a already set up double integral for a situation where we have z equals, which is exactly this one. So what we're going to do is we're going to select this equation, okay? Now, the vector p, q, r is our curl of f in this case, because again, we're dealing with this particular problem, this situation. This 13.6, it was more of a generic setup. So what we have here is 0, 0, and 1 plus 2y, okay? The partial of g with respect to x is the partial of this equation z with respect to x, which is 0, and the partial of g with respect to y is again of this equation, which is -1. So I hope this is making some sense. It's a lot to organize. So what we have then, if we utilize this equation right here, is that we have negative p is 0, because we just said that here, okay, so 0 is p, times the partial of g with respect to x, that's 0, minus q is 0, times the partial of g with respect to y, which is -1, and then plus r. So this double integral, because of all these zeros that we have, is really the double integral over d of really just what r was. It's just 1 plus 2y because of all the zeros. P is 0, q is 0, dg dx is 0. All right. Now, if we go back up to our diagram up here, the region D is actually labeled for us. It's this region in the xy plane, which is a circle centered at the origin with a radius of 1. So in this integral, it is best for us to convert to polars in order to solve this. So what we have is the double integral, 0 to 2 pi is theta, 0 to 1 is r, and then we have 1 plus 2 times r sine theta, because r sine theta is y, times r, and then we have dr d theta. So that simplifies to the integral 0 to 2 pi and 0 to 1 of r plus 2r squared sine theta, and then we have, again, dr d theta. Okay, I'm going to pause and work out the problem, and we'll be done. Okay, so there are antiderivatives, and if you notice, we do get the same exact value for this, and again, we're utilizing Stokes theorem. So was it shorter? Maybe not. It was about the same length, it seems like, but the idea of Stokes theorem applies to problems that we simply can't do with techniques from section 13.2 or with Green's theorem. So Stokes theorem opens the door to sort of the next set of surface integrals that we can do. Okay, the next video will be on example 2.